Okay, so now I'm starting part 2 of the lecture that's dated 8/1/2017. Alright, so I was in the middle of doing problems with inverse trigonometric functions. Okay, so let me just verify this is working properly first. Problems with, yeah. Okay, good. So I was giving you examples where you would use a calculator to evaluate inverse sine and inverse cosine and so on. So these were inverse sine functions here. Notice how this gave you an error because the argument was outside of the required domain, required interval -1 to 1. So for finding inverse trigonometric functions, inverse sine and cosine, you need the values of the arguments to be in that range, in that interval. Whereas you don't need it to be in that domain for the tangent function. So if I do it for the tangent function, I won't show it this time. Takes a bit longer for me to do that. So, but you try it at home. Inverse tan of say 1.5 is, and it gives you an answer. Inverse tan of 1.5 is 0.98 to 8 rounded off. So there it's in the domain because the domain is all real numbers. And I should say something more here. What I've done is I've put my calculator into radian mode. So I've shown that before, but there's a little, it's hard to see, but it's a little R there. So if you put this into degree mode, which you can do by going to the mode and my instruction book tells me, I just have to go. And now I do the same calculation, okay, after I change to degree mode, and now that gives me the answer 56.3099, etc. So rounded off to 1 degrees. Okay, so it'll give me a different answer if I'm in degree mode than if I'm in radian mode. But they're the same answer really, because they're just radian units and these are degree units. Units are degrees here. But the numerical answer from the calculator will be different. So if you're just going to be using radians all the time, then it's better to have your calculator in radian mode. Then you don't have to do this calculation all the time with going from degrees to radians. And notice if you take the tan of this, you have to be in radian mode, so it will recognize this as a degrees, this has to be in degree mode. Right, this is radian mode. This is degree mode. Okay, so if you take the tan of that, then you get back 1.5. But if you take the tan of that, then you'll get something else, not the right answer. 0.98 will give you 0.017. Okay, so if you forget to tell your calculator you want everything, all the angles to be assumed to be in degrees, or if you forget to tell it, here it's assuming it's in degrees, not radian, so you have to tell it to assume that it's in radian, otherwise it'll give you 0.017, which is wrong. So the correct calculation would be first put it in radian mode, so I'll go back to radian mode. And then it does give me .2. I'm just calculating that, and it's already 1.49. So it's approximate, but it's giving you the correct answer. 1.5. Okay, so you have to watch for that degree mode. It wouldn't matter what mode you're in. If you put in an answer that's bigger than 1, and for the sine inverse, then you would still get an error. Here it won't give you an error if you take the tan of whether it's in degree or radian. It will just give you the wrong answer, and you can't tell that it's the wrong answer. So yeah, that's why you have to be extremely careful about this. Make sure you check what degree, what mode you're in before you do a calculation, so you know what you're getting here. So some other another calculation is cosine inverse of 0.4. Use a different pen. Okay, so that's, again, a matter of just plugging it into the calculator. The answer should be, I'll be in radian mode now. And the shift cosine and then 0.4, let's see. So I get 1.159 or 1.16. So it's approximately 1.16 radian. So if I want the corresponding answer in degrees, which it could be since the output is, remember, an angle, then I would write, I could multiply by 180 divided by pi, or I could just, which I can do right now. Okay, that gives me 66.4 degrees. Okay. Or I could go back to the original problem and first put my calculator in degree mode. And then just do the original calculation over again. So inverse cosine of 0.4, and then I get same thing. Okay, so it doesn't matter which way you do it, but you should know how to convert anyway from radians to degrees if you need to, and also how to get back again, and just what are you getting when you put this kind of number into the calculator. You should check your mode, and then you can put the right units down, and then it will be a correct answer. Okay, so now let's do some examples. Oh, let's see. That wasn't the one I wanted to do actually. I wanted to do this one, cosine. If you put a minus sign in front. Okay, so the answer is not negative of these, right? Because this is not an odd function. So if you use a calculator, you'll see what you get. It's, I wrote down the answers here anyway. It's going to be pi minus this actually. Sorry, I got a call coming in here. Okay, just giving a lecture right now, so can't talk right now. So it's pi minus that actually. So it's about 3.1 minus 3.14 minus that. Why is it pi minus that? It's because of there is a kind of a symmetry here for the inverse cosine function. If I go into negative values, so here's a positive value. If I go to a negative value, it's just pi minus that value. This is pi here. So I just, the value if it's positive is here. To get the value when it's negative, I have to take that length and minus from pi, subtract from pi. And then that's the value if I just change the sign. Okay, so this answer will give me then 1.98. Okay, that's what I get using a calculator as well, 1.982 radians. If I use the degree mode with the negative sign here, then I'll get 180 minus 66.4, which is 113.58 or whatever, 113.6 degrees. And that's also what I would get if I put the calculator in degree mode first and then did this calculation. All right. Let's do another example, example 4. From the book, section 8.3, right? Okay, so here we have a triangle, and it's a right angle triangle. This angle is given as theta. We don't know what it is, but we know that two of the sides are, 9 and 12. And we need to find this angle. All right, so the way we find it is we construct a ratio and equate that to the corresponding trigonometric function. So remember how the trigonometric functions are built out of using ratios of sides. So what's the correct trig function to use? Well, because we have an adjacent and the hypotenuse here that are given, we could find this side also by using Pythagoras, but to make it even easier, we'll just use the corresponding trig function, which is a cosine. So the cosine of theta is the adjacent over the hypotenuse, which is 9 over 12, which is 3/4, or 0.75. Okay. Now to solve this, we just use the inverse trig function. Theta is cosine inverse of 0.75. Plug it into the calculator and use radian mode, and we get 0.723 radians. Or it's also, if you do it in degree mode, then it comes out as 41.4 degrees. Okay. So either of these answers is acceptable as long as you use the right units, radians or degrees. If you don't include units, I'll assume you mean radians. And then try it 4. Okay, well actually this problem we've seen before. Maybe not directly, but the solution will be the same as another answer that we had before. So now if you do it using the 10 on the hypotenuse, 10 is the length of the hypotenuse, and 6 is the length of the opposite side to the angle. Now the correct function to use is the sine function. So sine of theta is 6 over 10, which is 0.6. So if you take the inverse sine of 0.6, that will give you theta. And so we've done that particular calculation before. I think that was the first time I used the inverse trig functions and showed you how it worked. And you get this angle 36.9 degrees. So this is actually a 3, 4, 5 triangle in disguise. This side will actually turn out to be 8. All right. Finding exact values of the composite functions with the trig functions. Okay, so finding exact values of composite functions where where trig, or it's basically trig and inverse trig. Basically, one of these groups and others from the other group, and you combine them by composing them. So you could have a trig function on the inside and an inverse trig on the outside, or you could have inverse trig on the inside and trig on the outside. So we'll look at the different combinations we can have here. Okay, so let's try a different color. These colors aren't really named. I don't know what to call these, but this looks like blue, light blue. Okay, so here's one combination. Remember, if we take this combination, we take the inverse sign first and then the sign. That's equal to x as long as x is in the interval from -1 to 1, right? Because that's the required domain of the inverse sine function to start with. But the output of that will be the same as, it'll be an angle, and then you can take the sine of any angle. So the output, once the output is defined, then the next function will then also be defined, and then you will get this value. But that's only if x is in this initial starting domain. And you could say the same thing for cosine of the inverse cosine of x. It's going to equal x, and the tan of the inverse tan of x is equal to x. You just have to be in the required domains. This has to be in -1, 1, and this is different. X has to be in it can be any real number. So this is true. This is an identity for all x, for all real values of x. Now when you change them around, I mentioned this before, but now you have to be really careful because x is defined for, x will give you a value for sine, no matter what x is. It will always give you a value for the sine of x, right? But the question is, does it give you back x if you take the inverse sine of that? The answer is yes, only if, though, x is in the required domain of the inverse function of this sine function, such that you want the domain to be the restricted one corresponding to the inverse sine. In other words, you want to restrict that sine function to just the conventional one, so that when you take the inverse of that, you get the arc sine or the sine inverse function. Now it's going to be from -π/2 to +π/2. So because the domain and range change, that's going to also be the output or the range of this inverse sine function. So that makes sense because that's equal to x again. Okay, so it has to be in this domain, and then we have similar restrictions for the other two. Now we'll look at cases where x is not in that domain, and you'll still get a value. So if you put that in the calculator, you'll still get a value, but it will be different. So we'll look at examples on how to calculate that correct value. First, I'll write these down. Now the restriction is x has to be in this domain, because that's a correct domain for the cosine function before you take its inverse. Okay. It gets chopped off here. All right. So then tan inverse of tan of x. This is equal to x if x is in -π/2 to +π/2. again, because we're taking the middle, the central repeating part, the central part which is repeated to make the whole tan function, you just take that part. It's nice to take this part because it's connected. You go from minus infinity as you approach this boundary, and it comes down to 0 and then goes up to plus infinity smoothly. There's no interruption with an asymptote within this interval. So it's a very obvious, convenient choice to take for the restricted domain, so you can take the inverse tan as the inverse of that function. Okay, so now we want to also do, we want to calculate some things not, so if you're given this sine inverse and then sine of pi over 4, so you should check this is in the correct range, or the correct domain, right here. You're starting with an angle, taking the sine of it, getting a real number. Real number, you take the inverse sine of that, and then you get back the angle. So it's the same as before, as what you put in, because this is in that domain. It's just less than pi over 2, and positive. But if you take sine inverse of sine of 3 pi over 4, that's not equal to pi over 4, because it's not, 3 pi over 4 is not in this domain. I'll sometimes use this means contained in, and not slash means not contained in. Sometimes you find me, probably caught me trying to write that down, but I will explain at least what it is, because it is kind of a useful notation. This means pi over 4 is contained in this set, 3 pi over 4 is not contained in this set. It's just an epsilon, a Greek letter, corresponding to E. In the English alphabet. Okay, so what is this? What is this number then? The way you get this number is by replacing this angle with another angle, an angle this time in the range that you want, which doesn't change the value of the sine of that angle. Okay, so I can change this. If I look at my circle, the sine of an angle, the sine of 3 pi over 4, 3 pi over 4 is positive, so it's got to be in the upper half plane, either in the first quadrant or the second quadrant, because that's where y is positive. And it's not in the first quadrant because it's out of that range, clearly. It's in the second quadrant. It's right here. So if I just replace this 3 pi over 4 by pi over 4, I don't change the sign at all. And then I'm in the right range, in the right domain, and I can just equate that. And that is equal to, sorry, that was not equal to 3 pi over 4. That's what I meant to say. It's equal to pi over 4. Okay. So let's say that again. So if the value that you plug in is not in the correct domain, then the result of taking the inverse sine of that is not going to be equal to the original value. To get the correct value, this is equal, so this whole thing is equal to this here. So that's the answer. So to get the correct thing, you replace the argument here with another angle, and it will be in this restricted domain now, and this angle has to be such that the sine of that angle is the sine of the original angle, so it doesn't change the value of the sine function. Then once you get that in the right range, then you can simply you do the calculation by this identity here. It's equal to the x that you had inside. Okay, now that's doing the inverse sine. I'm sorry, that's doing the that should have been this one. You're doing the trig function first, and then the inverse trig function on the outside. Okay, so and let's try doing the trig function, inverse trig function first, and then the outside, and then the trig function last. So what's this? Well, this is in the required domain, -1 to 1. All right, that's the only restriction, and so this is equal to 1. So that's all you need to do. But if this is inverse sine of 2, then this is not defined. Because you don't get past the first step of taking the inverse sine of 2. It's not. It gives you an error. Okay. Let's try sine inverse. Let's do cosine inverse. This is example 5. Cosine inverse of cosine minus pi over 3. Now this minus pi over 3 is not in the correct domain of required here. So you see that that should be 0 to pi. Minus pi over 3 is negative. So it's not in that range. It's only positive values in that range, up to pi. But you can change this, again, you can change the value of the angle into another angle which gives you the same value for the cosine and is in that range. So this is what I have here. So here's my angle. It's minus pi over 3 is like this. It's minus 60 degrees. And what's going to give me the same value for the cosine? Okay, the cosine is the x component. So if I reflect this to the x-axis, it will not change the x component here. So this becomes, right, this is 1/2 minus root 3 over 2, and this will get reflected to plus 1/2 plus root 3 over 2. So what I'll get here is just the cosine is 1/2. But I can replace this cosine of the angle is 1/2, and then the inverse cosine will be just this value, which is plus pi over 3. Okay, so how I get that basically is I realize cosine is an even function. I can replace minus pi over 3 inside by just positive pi over 3. That does not change the value of the function, cosine. And then that is in the correct range, and then I can write down the answer as pi over 3 from here. Okay, so there's that way to do it. You replace it with an angle which gives the same value for the cosine, or you can just calculate it out. Do each step separately, and that's another way. You should get the same answer each way. Let's try it number 5. Tan inverse of tan pi over 8. That is pi over 8, because pi over 8 is in the correct domain to start with. So there you don't have to do anything. So that's the easy one. And then you do tan inverse of tan of 11 pi over 9. So remember what the correct domain should be. It should be minus pi over 2 to plus pi over 2 for the tangent function. And then you can take the inverse of that function. always remember the domain, especially the first function that you, when you take a composition. That's an important thing to remember. Otherwise, if that first x is not in that domain, then you can't start at all. So this again is not in this domain. Pi over 9 is definitely bigger than pi over 2. So you replace it with, well, you can use the periodicity of the tan function, and you can replace it with this value plus or minus pi. So subtract pi because it's bigger than pi. So 11 pi over 9 minus pi is 2 pi over 9. Is that in the correct range? We just have to check to make sure, but yeah, 2 over 9 is smaller than 1 over 2. So this is less than pi over 2, and it's positive, so it's within this domain. And so we can just rewrite this as tan inverse of tan of 2 pi over 9 now. And then we can use this identity, and it's just 2 pi over 9. So that's the answer. All right. Okay, so now let's do let's do another kind of problem here. Okay. So now I want to consider combinations of this form where you have the inverse of a trig function on the outside, and on the inside you have just a trig function, but they're different trig functions. So far we've been doing f and g are the same here. Okay, so these would be things like sine inverse of the cosine of a value. Say it's an angle, so we could call it theta. Okay, so there you'll definitely, normally not, you can't just write this as theta. You can't do a decancellation. But what can we say, how can we get this answer? How can we get a simple answer, actually? Here. So it's not as simple as theta, but it still is pretty simple. Okay, so let's see how we can do that. We'll look at a triangle. Where we'll call this angle theta. And so we're given theta, and if we know the side length here is 1, then we can fill in the other sides as it must be cosine theta and sine theta. How do we get from the value of cosine theta to the value of, to get the angle corresponding, so that the sine of that new angle is equal to the old cosine of the old angle? Okay, so what I'm doing here is I'm calling this x, sine inverse of x, where x is equal to cosine theta. All right. So this is now going to be some new angle phi. So how are phi and theta related? Well, if I look at this equation, sine of phi is going to equal x now. But that's the same as cosine of theta. So cosine of theta is equal to the sine of phi. Okay, well, when is the cosine of an angle equal to the sine of a different angle? Well, we saw something like that before, because we saw before that if you take the sine function and shift it to the left by pi over 2, then you get the cosine function. Okay, that's pi over 2, that's 0. right? So this is pi over 2 here. So you shift it by 2 pi, by pi over 2, sorry, and you'll get the cosine function. And we had a relation that allowed you to do that. So the cosine of let's call it alpha, let's call this alpha, is equal to the sine of alpha plus pi over 2. So remember we had that relation. That means that if you shift the sine function but to the left by pi over 2, you just add pi over 2 inside there, and then that gives you cosine. And we can verify it another way by using the complementary angles formula. So the cosine of alpha is equal to the sine of pi over 2 minus alpha. And that's the one I want to use here. So this can be written then as sine of phi is equal to the cosine of theta, which is equal to sine of pi over 2 minus theta. All right, so we can do this by taking a value of phi, which is equal to pi over 2 minus theta. Okay. Or either this will do, or we'll have to, we'll have to be careful, because what we want in the end is we want a simple formula here. So what I want to do is take an angle theta, which is in the correct domain of the cosine function. The correct domain of the standard domain of the cosine function is 0 pi. All right? Now, if we take this value, then so if I have another value not in that, then I just choose an equivalent value which is in that range, and it will still give me the same value for cosine. So let's call it theta prime. It might be different from the original value, so that cosine theta is equal to the cosine of theta prime. Okay, now the theta prime is in this correct domain. So if theta prime is in this domain, then phi, all these are primed now, phi is in pi over 2 minus these values, and that will be, you can see you are taking the negative of this, so it's from minus pi to 0, and then you're adding pi over 2, so it's minus pi over 2 to pi over 2. If I take the one extreme value, then I put it in, I get pi over 2, I get this endpoint. If I take the higher point here and I put it in, then I get the lower point. Okay, so phi is in this range. But that's exactly what I should get if I get an output for the sine inverse function. Okay, so that's telling me that this should equal to pi over 2 minus theta prime. Okay, so just to repeat it, so this requires that I pick a value theta prime, which is in this domain, required domain for the cosine function, and for which cosine theta is equal to cosine theta prime. Once I get such a theta prime, then I simply, to get this value for the entire function, I just take pi over 2 and subtract theta prime. Okay, shall we see how this works? So let's try it with sine inverse cosine of 13 pi over 6. So just to say that this also works for cosine minus 1 sine theta. So again, now you choose a theta prime in the required domain for, or the standard domain for the sine function, which is minus pi over 2 to pi over 2, such that sine of theta is equal to the sine of theta prime. And then I would just get as an evaluation pi over 2, same formula, but it's with the theta prime in it rather than the theta. All right, so let's see some examples here. Example 6. Evaluate. This is in the section still in 8.3. Evaluate sine inverse of cosine of 13 pi over 6. Pi over 6 is that in the range that, or in the domain of the cosine? Is that in the domain? And the answer no. See that because this is bigger than pi. Okay, so what would be an equivalent value here which would keep the cosine of the angle the same, but now be in that domain? Okay, well you can subtract 2 pi from that, and that won't change the cosine because cosine is periodic with period 2 pi. And when I do, I get 13 minus 12, which is 1. 13 minus 12 pi over 6. So it's just pi over 6. And that is in this domain. So that's my theta prime. That's what I want to choose for theta prime. And so I get sine inverse cosine of pi over 6 equals, and then to get the output, I just take pi over 2 minus pi over 6, which is 3 pi over 2, 3 minus 1 is 2, 2 pi over 2 over 6, which is pi over 3. Okay. Or another way of doing this is just directly evaluate. With the calculator, you can do it as well. You can just check these numbers and do it with the calculator. If you're asked to do it without a calculator, then you could still do it by using this is a spectral angle, and you just use the method for finding the cosine of that angle. It's a cosine. Anyway, it's the same as cosine of pi over 6, which is root 3 over 2, and the inverse, sine inverse of root 3 over 2 is pi over 3. Okay, so knowing the spectral angle values for the trig functions is helpful here if you want to do it that way. Now let's try it number 6. So now you do the inverse cosine of okay, I'm going to have to skip some of these because I don't have much time now. Sine inverse, or cosine inverse of the sine of minus 11 pi over 4. And so the question now is this in the correct range? Okay, so it's different from this, different from that one. Here I want this to be in minus pi over 2 plus pi over 2. And this is not, so I have to add. Let's try adding 2 pi to that. And that won't change the sine function because it's periodic with period 2 pi. So it's 8 minus 11 minus 3 pi over 4. Okay, that's still outside the range. So now let's check the situation here. So we have minus 3 pi over 4 is about 3/4 of the way here. It's over here. 3/4 of the way to 180 degrees, minus 180 degrees, or minus pi. So it's this angle, and to get the same value for the sine, we have to just put it in this quadrant. So that's going to give us minus pi over 4. So this is the same as sine of minus 11 pi over 4 is the same as sine of minus pi over 4. So that's what we would use, that angle. So this whole thing here is cosine inverse of sine of minus pi over 4. And we get it by using the formula now. Pi over 2 minus negative pi over 4 is pi over 2 plus pi over 4, which is 3 pi over 4. All right, so now let's do one more page here. This is going the other way. F composed with g inverse. So now we want g to be an inverse trig function and f to be a regular trig function. Okay, so let's look at an example. Sine of cosine of minus cosine inverse of 4 over 5. Okay, so how I would do this in general is I would let this thing now, which is an angle, let that equal to something. Call it theta, so it looks like it should be an angle. So let theta equal to the inverse cosine of 4/5. That means cosine of theta has to be 4/5. Okay, now we know one thing, that theta has to be in this domain, or this range for the inverse cosine, 0 to pi. But we also know another thing. This value, positive value for the cosine means that, in particular, you can't go into the negative. You can't go into the region where the cosine is negative. The cosine is negative over in the second quadrant. So it has to stay in the first quadrant. So we know in particular that it's even more restricted than that. It's in the interval 0 to 2 pi. But that's allowed. Now we're allowed to. Well, we can take the sine of anything that we get, but we can look at a diagram to get the sine of this theta. Okay, so let me recap so far. We have a composition of two functions. First, on the inside we do an inverse trig function, and then we do on the outside a regular trig function. The inverse trig function, I define it to be something new, like call it theta, a new variable called theta. Theta has an exact value, which we don't actually need to calculate here. Let me point that out. But we know its cosine is equal to 4 over 5. Now the answer to our problem will simply be to evaluate the sine of that same angle, sine of theta. So how do we get from the cosine, if we know it, to the sine? Well, we can draw a triangle, and we can show this all in a picture. Here's my angle theta. The cosine, if I know it's 4 over 5, then I can draw a triangle which is 4 on this side and 5 on this side, and that will work. Because it's it's similar to every other triangle with this angle. We could also choose 8 and 10, but we'll still get the same final answer. The sine of the angle will also only depend on the angle theta and not on the actual lengths of the sides. How do we get the sine of the angle? Well, we take the opposite side and divide by 5. But what is the opposite side here? Well, you can recognize this is a 3, 4, 5 triangle, or just use Pythagoras. 5 squared minus 4 squared, square root is 3. That's how you get that side. Okay, so, and then you can get the final value for the sine. It's 3 over 5. And that's my answer. Okay, so what is this in general? So if you're evaluating sine of the cosine inverse of x. X has to be in the domain -1 to 1 for this to work. Okay. And let's also assume that x is positive here. So this is a bit of a restriction. But if x is negative, then it actually doesn't change things very much here at all. If x is negative, then the angle will. Okay, well, we'll see what happens if x is negative. So assume x is positive here. So then we can draw a triangle. We can call this theta, and then in this triangle we'll have a 1 here and an x here because the cosine of theta is x. Okay, that's the way I define theta. Theta is a cosine inverse of x, therefore cosine theta is x. And so the remaining side, that means I can choose a triangle where this side is x and this side is 1. And the remaining side is by Pythagoras 1 minus x squared. And so the sine of theta will then be just by this triangle. That's my answer, and it's going to be just the square root of 1 minus x squared. Okay, and that will be how I get this 3 over 5 as well. But I can do it if I put in any value between 0 and 1, then I could use this formula to get it. Okay, so what if x is negative here? So x is in -1 to 0. Okay, so then I replace cosine inverse x by theta, where cosine of theta is equal to x. Now, theta we want to be in the correct. Let's see. Yeah, so if you evaluate sine theta, you see, okay, what happens is sine theta could be plus or minus the cosine of theta, 1 minus the cosine of squared of theta squared. So it's when we take the square root that we have an possible ambiguity. Okay, so this is going to turn out to be x. So in terms of x, this whole thing will be plus or minus the square root of 1 minus x squared. Okay, so if x is if the cosine inverse of x is negative, sorry, if x is negative, then the cosine inverse of x, that's an angle that's going to be between pi over 2 and pi. So it's going to be an angle in this quadrant 2. All right. Now what does the sine of that have to be? The sine of the angle, well, it's still positive actually. So I end up having to choose a positive root anyway. There's no change there. Okay, so it's the same formula as before. All right, so we have a little bit of, we have to think about that to get that, but it's not as hard in some of these cases here. Okay, so let's try another one. Try Try number 7. So you have to think about these sort of on an individual basis in each case, possibly. So I'll just do a couple more of these. Try number 7. I get the cosine of the inverse tan of 5 over 12. All right? So the cosine of tan inverse of 5 over 12, so again, the idea is you call this theta, so you introduce an intermediate variable. Theta here is going to be an angle between 0 and 2 pi because this is a positive real number. Sorry, between 0 and pi over 2. Okay. So the inverse tan is up here. This is between 0 and pi over 2. Okay, so that means the tangent of theta is 5 over 12. Okay, now let's just construct a triangle which has an angle theta with that value of the tan. So that means, you know, I'm not drawing it accurately, but it's going to look something like this, I guess. But this side should be 5, and this should be 12. And then that will give me the correct value for the tangent of this angle, theta. Well, if that side's 5 and that's 12, then what's the third side? Well, you add the squares, and then take the square root. So it's 25 plus, that's 144. So this becomes 169, which is square root of that is just 13. So this side is 13. And from that, we're asked to construct what trig function of theta? It's the cosine of theta here. So we just look at this ratio, and it's 12 over 13, and that's it. That's the answer. Let's do try number 8. Here we have cosine of sine inverse of 7 over 9. Okay, again, call this angle theta, call this intermediate result theta. Draw a triangle where the sine of theta is defined as now 7 over 9. It's going to look like something like this. Here's 7, here's 9, opposite over hypotenuse. This was, by the way, opposite over adjacent. So opposite over hypotenuse is 9. And the remaining side is you use Pythagoras to get 9 squared minus 7 squared. So that's 81 minus 49, which is square root of 32, which is 4 root 2. Okay, so this side is 4 root 2. And the cosine of theta is 4 root 2 over 9. And that's all you have to write, and that's going to be the answer. Okay, I checked these with the answers to the back. The answers to the back are consistent with all these so far. Now let's try one more, and then just call it quits after this. So try at 9. Try at number 9. Find a simplified expression for sine of tan inverse of x, of 4x. So a simplified expression for sine of tan inverse of 4x. Okay, so x could be possibly positive or negative. And it could be any real number because that's in the domain of the inverse tangent function. So again, we call this theta. And then we look at the triangle that we get there. So let's first assume that x is positive. Okay, so we look at our triangle, and now it's just a regular triangle, and these side lengths are all positive. Here's theta, here's 4x, and this is going to be 1. So what's the final side, the hypotenuse? It's the sum of the squares of these, and then take the square root, so it's 1 plus 16x squared. So we have to write that expression down. We cannot simplify that any further. And what are we asked to find? We're asked to find the sine of this theta. Okay, and that's just 4x over, in this case, 4x over 1 plus 16x squared. Okay, so that's a simplified expression, but so far it only holds for x positive. So that's half the values that we can possibly put in there. So case 2, what if x is negative? Okay, so now can you see that there's a good way to simplify this? And that is, we notice that the tan function is odd. The inverse tan is odd too. And the sine and the inverse sine are both odd functions as well. So if I change the sign of the argument here, then I'll change the sign outside of the tan inverse, but still inside the sine argument. So the sine will come out of that because it's an odd function. And then because that's also an odd function, the sine will come out of that completely. So the sine will appear outside. And will it change the formula at all? And the answer is no, because if this changes sign, the x changes sign, then that does not change the denominator at all, because the square, the square just gets rid of any sign if it has one at all. And the answer will be numerically the same as if you put the negative answer in here. But this will change only by a negative sign, and that's just what we want. So it's like we'll get a negative angle. This side will go below the horizontal axis. This point will go below the horizontal, and that's how I can interpret this as a negative side. But the other two sides will both be positive. Okay, so the same formula holds. So that's the answer for any x. For any real x. Okay. So that's all I would like to do for now. I've done quite a bit, and hopefully you're doing well practicing for the quiz coming up on Monday. We'll have to have that. We'll have to have just on Monday, so please be ready for that. And a final word is I'll try to get an assignment as soon as I can out on the trigonometric stuff. But this finishes off our chapter 8 stuff. And I will do, like I said, a little bit of chapter 9 and 11, the basic things of chapter 9 and 11 for you. And so hopefully that will take only like maybe 3 lectures to do. Okay, so with that, have a good day. Take care. Hudofes.